So if you remember back to one of my older videos, we discussed how to determine whether a normal one variable equation has one solution, many solutions, like all solutions, or no solutions. And you can sort of picture how each of those equations looked. If you remember, it was like one solution. It had like a normal answer like x equals a number. For no solutions, it would give you an untrue statement, like something like 0 equals 3, which is just straight up not true. Or for all solutions, you would have something like x equals x, or maybe 1 equals 1, 2 equals 2. For any value of x, you would get any solution. Oh no, for any value of x, you would get a normal solution. So that would make it all solutions. Well, it works somewhat similarly for systems of equations, except there are two variables and two equations in this case. So first, let's look at this left example that we have. And we have the equation y equals negative 2x plus 10. And the second one is 6x plus 3y equals 30. Now already I can see something that we can do with the second equation, and that is divide everything by 3. I see a greatest common factor of 3, so let's do that. So dividing everything by 3, we will get 2x plus y equals 10. And looking at this first equation, we can leave it as y equals negative 2x plus 10. So the method of solving that I'm going to use for this equation is substitution, because we already have the value of y, the expressional value of y. So I'm just going to plug that into this equation, and we are going to see what we get. So plugging negative 2x plus 10 in for y in the first equation will give us 2x plus negative 2x plus 10. And if we solve this out, we're going to see that 2x minus 2x, that just becomes 0. So we can get rid of that, and we see that all we're going to be left with is 10 equals 10. So this is a situation where we get a true statement, 10 equals 10. So therefore, the answer is going to be all solutions. And you're going to get the same thing when you plug it back in. Well, you can't really plug this back in, but you're going to get the same thing if you were to do this for x, or if you were to do elimination. Now, the question is, what would this look like on a graph? Good question. So let me get my coordinate plane here. And this one works. So we can graph both of these lines on the coordinate plane. So what is it? Y equals negative 2x plus 10. The y-intercept would be 1, 2. We'll do it in intervals of 2. So 2, 4. So 2, 4, 6, 8, 10. That's our y-intercept. And negative 2x, so that's a negative slope. It would look something like that. Alright, and now if we looked at our other line, 2x plus y equals 10, that's in standard form. So let me find the intercepts. Plugging in 0 for x, we get y equals 10. So our y-intercept in this one is also 10. And then if we were to do the same thing for y, so plug in 0 for y, we get 2x equals 10. Solving that gives us x equals 5. And you'll actually start to notice that the x-intercept in this line is 5 as well, because remember, we're doing intervals of 2 for a graph, and it crosses that half mark right between 4 and 6. So the x-intercept for this graph is also 5. So therefore, both of these lines are actually the same. So when you're graphing equations and you see that both of their lines are the exact same line, basically, That's how you know that you're dealing with a system of equations that has all solutions. So all infinitely many solutions are valid. Um, you can sort of start to notice it up here, really, when we divided by that 3 in the second equation. Normally, test makers will try to trick you by multiplying one of the equations by a number or a multiple that will sort of make it seem like it's an entirely different equation, but really when you look at it, it's just an altered form of that first equation, just because they multiplied the entire thing by a certain number or divided the entire thing by a certain number. So that is how you detect if a system of equations has all solutions. So for this one, we're just gonna write all solutions. And now we are going to move on to our next example. And our first equation in our system is going to be negative 5x plus 3y equals 5, and x minus 3/5 y equals 2. I'm actually going to make this a different color so that it's easier to see when we're graphing. I'll make it orange. Okay, so let's solve this out and see what happens. I see a fraction here. I think I'm gonna get rid of that by multiplying the entire equation by 5. Let me get an orange pen. Okay, so multiply this entire thing by 5, so that's gonna give us 5x minus 3y equals 2, or sorry, 10. I multiplied by 5 to get rid of the 5 in this denominator. And now we have negative 5x plus 3y equals 5 for the, what's it called? Top equation. Now, I'm going to use elimination to try and solve this. So if we were to add both of these equations together, oh wait, I forgot to put this in blue actually. Alright, so if we added both of these equations together, it would actually eliminate this variable. But now I'm seeing that at the same time, it would also eliminate the y variable. So let's see what happens. So adding these both together gives us, so that becomes eliminated, but then at the same time negative 3y plus 3y is equal to 0, so that becomes eliminated too. So then we're left with 0 on this side, and then if we were to add these together, we would actually get 15. And now we're left with another untrue statement, and this is where no solution comes into play. So this system of equations has no solutions because when we try to solve for one of the variables, we actually get this untrue statement. So now the question is, what does this look like on a graph once again? So if we get another coordinate plane here and we graph both of these lines, they're both in standard form, so let me find the x and y intercepts. The x-intercept for this one would be 2. So 2 is right there. And then the y-intercept for this one would be negative 10/3, which is around negative 3 1/3. So that would be right here. And then plotting that line, it would look something like, oh my goodness, it's really a pain to use this ruler. So now we can connect the orange dots and make our straight line. And then if we look and do the same thing for the other equation, negative 5x plus 3y equals 5, we see that the x and y intercepts are actually going to be different. So x, if we plug in 0 for x, then we get y equals 5/3 for the y-intercept. So let me draw arrows here first. But the x-intercept for this equation would be -1, I believe. Yeah, it would. -1. And the y-intercept, or sorry, the x-intercept for this would be negative. No, you would put 0 there. What am I saying? And then, wait a second. Oh, I said, okay, I'm confusing myself now. I said x-intercept, but I put that on the y-axis. That's why. Okay, forget all that. The x-intercept is -1, which is right here. And then the y-intercept would be 0. The y-intercept would be 5/3. Okay. And 5/3 is right around here. Sorry about that. So now we can plot our line again. And notice that I don't have to change the rotation of this ruler at all, because these lines are parallel. Now, because they're parallel, the lines are never meeting. They're never intersecting at any point. They're just going to be constantly going in the same direction, and they're never going to touch each other. And that means that the system of equations has no solution. Now, why are they parallel? Well, that's because they have the same exact slope. And to see whether they have the same exact slope, by the way, these two lines have the same exact slope as well. It's just they have different, or they have the same y-intercept, so they're basically the same equation. For this one, they're not the same equation. Although they have the same exact slope, they have different y-intercepts, and that's why you'll see that they're both parallel, but they will never touch. So how can we determine this from early on? Well, you can see that when I multiplied by 5 here, you had -5x plus 3y equals 5, and it looks very similar to this one, but we have the same expression, so to speak, on the left side, but on the right side we have different numbers. So when you see that you have that same expression, that 5x minus 3y, but on the right side you have like different numbers, then that's how you know that you're gonna have no solution, because you can't really manipulate one equation anymore to become like the other without sort of having all of the variables identical, so that you can eliminate one side, evaluate the equation for one variable. So that's why these lines will never meet. That's why you'll never see a solution for this. And yeah, that's basically how to determine whether a system of equations has all solutions or no solution. And if it's neither of these, then that's how you know that it's going to have one solution. So I hope you found this helpful, and I'll see you in the next one.